Hi, my name is Muhammad Ashir bin Wahab. My metric number is B1424100039. So for this assignment, my group is choosing Daikin VRV system. So here on this video, we will present about Daikin VRV system. This is my group members, myself, Muhammad Ashir bin Wahab. Here is Muhammad Aizah Akil, Muhammad Syami Aiman, Amu Tarasan, and Akasha. This is second order system intro. So here, as we can see, a second order system is defined by a differential equation where the highest power in the denominator of the transfer function is 2. Here's 4 points as we can see. First is output depends on acceleration, second derivative. Second, contain tuples in the S-plane. Third is behavior is governed by the damping ratio. Last but not least is critical for temperature and speed regulation.
Problem statement and the main objective of our project. First, let's look the problem. Traditional air conditioner system have a slow response when the room temperature is changes. Because of this, the systems keep switching on and off repeatedly when the waste energy and reduce efficiency. In addition, user may experience delay comfort because the temperature takes long to reach the deserved setting. Next is the main objective. First main objective to maintain the room temperature as close as possible to the deserved set point with only minimal variation. This helps provide a more stable and comfortable indoor environment. The second objective is reduce overshoot. Overshoot happen when the temperature exceed the target value for stabilizing. By minimize overshoot, we can avoid sudden cooling or heating spike, improve user comfort, and increase the overall efficiency of the air conditioner system.
Hi, Assalamualaikum. My name is Muhammad Syami Zulkifli. I will explain the block diagram of our Daikin VRV air conditioning control system. The system uses a closed-loop feedback control system. The input of the system is desired room temperature, also known as the set point. For example, the user may set the air conditioner to 24 degrees Celsius. The set point is sent to the controller, which compares it with the actual room temperature. If there is a difference between the desired temperature and the actual temperature, this difference is called the error signal. The controller then sends the control signal to the air conditioning system, specifically the inverter compressor. The compressor changes its operating speed to cool or heat the room until the desired temperature is achieved. The output of the system is the actual room temperature. Finally, a temperature sensor continuously measures the room temperature and sends this information back to the controller as feedback. This feedback allows the controller to make continuous adjustment so that the room temperature remains stable and close to the set point. Overall, this closed-loop control system improves temperature accuracy, reduces energy consumption, and provides better comfort for the user. Moving on to the next slide, I will explain the system transfer function. The transfer function is a mathematical method that describes the relationship between the input and the output of the air conditioning system. For our project, the transfer function is Gs equals to 25 over S squared plus 6S plus 25. This is a second order transfer function because the highest power of S in the denominator is 2. For this equation, we can determine two important parameters. The first is the natural frequency, which is 5 radians per second. The second is the damping ratio, which is 0.6, since the damping ratio is between 0 and 1. The system is classified as an underdamped system. An underdamped system responds quickly to changes but has a small overshoot before reaching a stable value. Based on our calculation, the system has a peak time of 0.785 seconds, a settling time of 1.33 seconds, and a percent overshoot of 9.48%. These values show that the Daikin VRV system reaches the desired temperature quickly while maintaining good stability and avoiding excessive oscillation. Therefore, the transfer function confirms that our Daikin VRV system is a stable second-order underdamped system.
Hi and Assalamualaikum. My name is Ahmad Zakir, so I'm going to continue with the theoretical system dynamics, which our group has made a table and which shown the parameter and the manual result that we've been searching for. Yeah, the first one is our peak time, which is called TP. The manual result we get is 0.785 seconds. And the settling time is TS, which the manual result we got 1.33 seconds. And the next one is percent overshoot, which is the percentage of OS. We got 9.48% for the manual result. And the last one is damping ratio, which is 0.6, and is considered as underdamped because it is below than 1. So the next one, I'm going to continue with the MATLAB simulation result. So as we can see on the right side of the picture, we have the coding that we create using a MATLAB. And the left side is the graph that shown after we run the coding. So as we can see, we got the Daikin VRV system state response graph. And the graph has shown the rise time, peak deviation, overshoot at what time, and the transition time and the final value. So that's all for the MATLAB simulation result.
Assalamualaikum warahmatullahi wabarakatuh. My name is Akasha bin Muhammad Talib and my metric number is P142410427. For this slide is steady state error analysis. For number one is a position constant. So the steady state error that we all get is 0.5, and for the velocity constant, steady state error that we all get is cannot be traced. And for the next is acceleration constant. Also, steady state error that we all get is cannot be tracked. Next is a stability conclusion. So, overshoot of transit in the system is found to be very satisfactory at the value of 9.48%. This is a good balance between speed and overshoot of the system. Next is a system intersect occurring satisfactorily in around 1.2 seconds, hence rapid convergence without any oscillation. And lastly is a perfect agreement of simulation with the model proven that mathematical consistency of the model of the controller. Thank you.